Hopefully when you read about the electromagnetic spectrum in yesterday's assignment, you realized just how teeny tiny the amount of light that we can actually see is within that spectrum. Everything from infrared to ultraviolet rays to gamma rays to X-rays. There's a huge range of different types of light waves, and there's such a small portion of them that we can see. As we go forward and talk today more about the energy of light, the energy is what's going to really help us to understand the atomic structure, which is where our ultimate goal is in this chapter here. So you will remember from before, we talked about how the frequency and the wavelength of light are related to its speed. And we had two different forms of the same equation that we were using. And we noticed that the relationship between wavelength and frequency was inversely proportional. We said that if wavelength goes down, frequency has to go up. If wavelength goes up, then frequency has to go down. And what it's important to keep in mind here is that this number is always a constant. The speed of light is always a constant. Now we have another relationship today that helps us get a relationship between the energy and the frequency. Now, in this particular equation, the H, E equals HF, the H is what the constant is, and it's called Planck's constant after the gentleman that discovered it. And Planck's constant, again, just like the speed of light, is a number that's not going to change, and it's a number that you do not have to memorize because you'll be given it anytime that you need it. So, the speed of light and Planck's constant are always the same. And so now, if I take Planck's constant times the frequency, I'm going to come up with the energy. So what happens if the energy goes down? What happens to the frequency? Well, I'm going to do a similar example like I showed you in the last video between frequency and wavelength to try to show you how this works. In this one, the H is the one that's always going to stay constant. So let's say that I use the equation 6 equals 2 times 3. In this one, the 2 is what I always want to remain constant. So let's say that I take this number and I make it go up. So I'm going to take the 3 and I'm going to make it get bigger. Well, what happens to this? Well, 2 times 4 is 8. So that one got bigger also. What happens if this stays the same and I make the 3 go down? So maybe I take it down to 1. Well, 2 times 1 is 2. So if the 3 went down, the 6 went down also. So this relationship is called being directly proportional. So what we want to do is we want to carry the relationships that we learned the last time just one step further. If the wavelength goes down, the frequency goes up. If the frequency goes up, the energy also has to go up. Okay? If the wavelength goes up, the frequency goes down. If the frequency goes down, the energy also goes down. And so you're going to be doing some homework problems where you're going to be talking about that. But this is a relationship that you really need to try to get pretty solid in your mind. And for me, the easiest way to remember it is to look at the equations and say, okay, if I make this number bigger and this one stays the same, what's going to happen to this other variable that's over here? Okay. So again, those relationships are very, very crucial when we're talking about the structure of an atom and what we're going to be going into next. So really try to get that down. Let's do an example problem with this new relationship so you can see how that works. A light wave has a wavelength of 0.00121 nanometers, and I want to find out what the energy is. So just like the problem that I worked in the last video for you, if the wavelength is given in nanometers, my speed of light is given in meters per second. So the first thing I'm going to have to do is I'm going to have to change this into meters so that I can get everything into the same units. So I'm going to start with 0.00121 nanometers. And you'll remember that 1 nanometer is 1 times 10 to the minus 9th meters. So nanometers will cancel out, and I will end up with 1.21 times 10 to the minus 12th meters for my wavelength. Okay, so this is what wavelength is. It asked me for energy, but I don't have wavelength in this equation. I do, however, have wavelength in this equation. So this is the only one I'm going to be able to use because I know the speed of light, it's a constant, and I know the wavelength, so I'm going to be able to find the frequency. So I'm going to use, since I'm trying to find frequency, it would probably be easier to use this equation over here. So frequency equals the speed of light over the wavelength. So I have 3.00 times 10 to the 8th meters per second divided by the wavelength I already found, 1.21 times 10 to the minus 12 meters. So again, meters per second divided by meters is going to give me units of per second, which is the same as a hertz. So when you type this into your calculator, you should end up with 2.48 times 10 to the 20th hertz. Okay. Now that I know what the frequency is, now I'm going to be able to find the energy because I know the frequency and Planck's constant, and so I'll be able to find the energy. So if energy equals Planck's constant times the frequency, Planck's constant from up here, 6.63 times 10 to the minus 34th joule seconds times a frequency of 2.48 times 10 to the 20th hertz, which is per second. And then if I write it like that, you can see that these seconds actually cancel out and I'm left with units of joules. And so I will have a final answer, and it will need to be in 3 significant figures of 1.64 times 10 to the minus 13th joules. Okay. So when you're working these energy problems, depending on what you've been given, basically what you need to remember is the C, the speed of light, and the H, Planck's constant, are always constants. You know what those are. And so you're going to have to say, well, what did they give me? And which equation can I use based on the information that I have? Sometimes you'll have to use one in order to be able to find the other one. So it may take a little bit of trial and error, but you only have 2 equations to use and you have 2 constants. So if you get everything plugged into the right spot, you shouldn't have too much trouble with these problems.